So today we're going to continue talking about imaging. Last Tuesday, on Tuesday, I talked mainly about imaging using X-rays and the conventional sort of X-ray, which chest X-ray, which leads to a projected image, and so you understand the limitations of projected images. And from X-rays, something about the physics of how an X-ray image is formed based on X-rays passing through your body, and depending on what tissues, what types of tissues the X-ray passes through, some of that X-ray energy will be absorbed, and therefore only a fraction of it is available to pass all the way through your body and expose the X-ray film. And we're going to talk about several alternate forms of imaging today, many of which are similar to CT imaging. Now, CT imaging is a special form of X-ray imaging where you rotate the source of X-rays and the detector around the object you're trying to image, around the patient, and you take images at a large number of angles, and using mathematical approaches, you reconstruct the three-dimensional image from those multiple two-dimensional projections. Right? And that mathematical process is called reconstruction from back projections, and it results in a three-dimensional image. In a CT, a slice of the object of the patient is obtained by rotating the source and the detector around that axial location. What we're going to start with is talking about an alternate to CT. What happened? Did it go out? It was on at the beginning, right? We're going to talk about an alternate to CT that doesn't use there. It's there, but not good, is it? Sorry, just take me a minute here, hopefully. Does that look better? Well, we'll go with it anyway. That looks a lot better. Okay, we're going to talk about an alternate to CT, which forms the same kind of images. That is, images of an axial location, maybe a transverse image, a slice from the body will be imaged using a technique called magnetic resonance as an alternative to using X-rays. And we talked last time about one of the problems with X-rays, that X-rays had a lot of beneficial qualities for making images. They pass through tissues, they allow you to look inside, they're absorbed selectively by tissues of different density, they're able to expose X-ray film, and all of those properties make them very good for forming images. The problem is that X-ray radiation is a form of ionizing radiation. It that can cause damage to cells and tissues in the body. And so one has to be careful about how much dose you expose a particular patient to. In magnetic resonance imaging, you use magnetic fields and radio frequency radiation non-ionizing forms of radiation in order to form an image. But the kind of image you form is the same. You form a three-dimensional image of objects, but since the physics is different, the things that create contrast or your ability to see one object from another in an MR image are different than in a CT image. In a CT image, what forms the contrast is the absorbance of X-rays by the tissue. And so your lungs, which are mostly air, allow X-rays to pass through relatively easily. And so they're different from soft tissue like blood or the muscle tissue of your heart, which absorbs some of those X-rays. And they're different from bone, which absorb a lot of those X-rays. And so it's density of the tissue, absorbance of the X-rays that leads to contrast. One of the things I didn't talk about last time was that sometimes physicians, when they want to make images of objects where there's not a lot of intrinsic contrast, like say you want to look at the intestine, but if you take an X-ray of the abdomen, everything appears like soft tissue. Everything looks about the same. If you, however, fill up the intestines with air, if you fill up the intestines with air by feeding air to the patient or by somehow getting air into the intestinal tract, then that image will appear dark where that air is. And you can create contrast. You can see what's inside of the intestine that way. Another way you can do it is by having the patient drink something that absorbs X-rays very readily. And that something is usually a solution of a barium, a colloidal barium solution that's very X-ray dense. So you can create contrast that way. That's a digression, but something I didn't mention last time and is mentioned in the chapter. What I want to talk about MR is a different way of forming images, uses a different kind of physics, and so the elements of intrinsic contrast are different. We'll talk about what makes MR images in a few moments. But bone does not appear well on MR images, whereas bone appeared very well in X-rays and CTs, for example. So if you've taken some chemistry rather, in college or in high school, you've probably heard of NMR, nuclear magnetic resonance. It was discovered by chemists as a way of analyzing chemical samples. And it turns out that if you put certain nuclei, if you put certain atoms in a magnetic field, some of them will align with the magnetic field because they have a magnetic dipole. Atoms have a magnetic dipole. So hydrogen atoms or protons have an odd number of nuclei, of neutrons or protons. Because of that, they have a dipole, a magnetic dipole. You put them in a magnetic field, they will align with that magnetic field. And if you then perturb the molecules that are aligned with the magnetic field using radio frequency waves or other magnetic fields, we'll talk about this in a moment, then you can measure something about the properties of the atom. And chemists use this because it turns out that if you align all the hydrogen atoms or protons in a sample, if you align them in a magnetic field and then you stimulate them with the right kind of radio frequency, they will respond by producing a radio frequency of their own, by producing an energy emission of their own. That energy emission is at radio frequency wavelengths, and you can detect it. And protons that are in different environments will respond slightly differently. So a proton that is, or a hydrogen, I'm going to say proton instead of hydrogen atom because that's easier to say, or hydrogen ion. A proton that's in a fatty solution will behave differently when stimulated in a magnetic field than one that's in water. And one that's in bone will behave even differently than that. So the properties that you can measure by this process called nuclear magnetic resonance depend not only on the atom that you're stimulating, hydrogen in this case, but the microenvironment or local surrounding that the atom finds itself in. And so if you talked about this in chemistry, you might talk about distinguishing different hydrogen ions that are associated with an alcohol molecule, or with a benzene ring, and how ones that are in different positions on the molecule will actually respond differently, give you what chemists call different chemical shifts. So it's that same phenomenon that's being used here to create images. And it was discovered in 1946 that atomic nuclei could absorb and re-emit radio frequency energy, and particularly when they were aligned in a magnetic field. And that led, this discovery of the nuclear magnetic resonance concept led to the Nobel Prize in Physics in 1952. It's called nuclear magnetic resonance because it involves, it depends on the particular properties of the nuclei of atoms, that is the number of protons, the number of neutrons. It's magnetic because a magnetic field is required in order to align the ions. And it's called resonance because you're looking for a resonance between the excitation of these molecules, these aligned molecules, aligned in a magnetic field, but you're exciting them with radio frequency waves. And you're looking for a particular resonance between the magnetic field that's applied and the stimulation that you give with radio frequency. Now, when I was introducing the subject, I didn't call it nuclear magnetic resonance imaging. I called it magnetic resonance imaging, or MRI, and that's the common name that's used for making medical images using this particular physical approach. And why do you think the name was changed from nuclear magnetic resonance to MRI during the 1980s when this technique started to be used in people? So anything with nuclear doesn't sound so good. You don't want anything with nuclear done to you, probably because of other uses of nuclei and concerns about nuclear sources of energy and that kind of thing. So the name was changed, but I don't want you to be confused because the phenomenon is the same. So to perform magnetic resonance and to make magnetic resonance images, you need a very strong magnetic field. And magnetic fields, if you remember from physics, are measured in a unit called Tesla. And most of the clinical units that are used to perform magnetic resonance images have magnetic fields ranging from 1.5 to 4.0 Tesla. And a Tesla, another unit for that is the Gauss, and the conversion factor is shown here. But just to put it in perspective, you know that the Earth has a magnetic field. That's why compasses work, has a magnetic field. And so if you have a compass, which is just a device that detects the Earth's magnetic field, always aligns with north, for example. The magnetic field of the Earth is about 0.3 Gauss, and it ranges between 0.3 and 0.6. So a Gauss that would convert to 0.6 Gauss converts to 60 microtesla, right? So 60 times 10 to the minus 6th Tesla is the magnetic field of the Earth. We're talking about much, much higher magnetic fields than that, right? And so you'll need to know this because you're going to go down and visit the MR Research Center at Yale this afternoon. And magnetic fields of this strength can interact with other magnetic objects like credit cards that you might have in your pockets or keys that you have in your pockets. And so when you enter an MR suite, you have to make sure that you're not carrying anything metal, wearing anything metal, or carrying anything magnetized that has a risk of being demagnetized with it, because these are very strong magnetic fields. Because of this, the MR facility that you will see here at Yale is in the basement of the Anlian Center, and usually these machines are in the basements. If you go to a hospital and you have an MR taken, usually you go down to the basement. And why is that? Because they're put in rooms that are specially shielded. They're specially shielded so that the magnetic fields cannot penetrate outside of the room. And that's so that people that are walking by on the street don't have their credit cards erased, right? People that are walking by in the street don't have metal objects pulled out of their hands, right, by the strong magnetic fields. And so this is one of the risks for people that work around nuclear magnetic resonance imaging, is that the fields are so strong that any metal object that's in the vicinity of the magnet can become a projectile. And so they're very cautious about metal. Another reason why we asked you not to take any stuff that's unnecessary with you when you go down to the Anlian Center this afternoon. So the magnetic fields are very strong. Anybody had an MR image taken? So Wilma, yeah. several of you. And so it was a device, might not look exactly like this, but looks something like this. So this looks similar to the CAT scanner I showed you last time, in that there is an instrument with basically a big cylinder with a cylindrical hole in the middle. And this hole, this is where the patient is going to go. The patient will be lying on this cart. And this will act like a conveyor belt that will move the patient inside the cylinder. And it's close fitting. You don't want the size of the cylinder to be too far away from the patient, because you want the magnetic field forces and the radio waves that are emitted by the atoms in your body to be very close to the detectors that are measuring it. And because of this, when you're inside, many people, Wilma, did you experience this? You feel claustrophobic when you're inside the machine because you're in a very confined space, and the images take some time to acquire. So the quality of the image depends on the strength of the magnetic field and how long you acquire the image. If you have more time to wait, you can get a better image. Right? And so there's a trade-off between building magnets that are incredibly strong, which is very expensive, and time for the patient to be inside the instrument to acquire an image that has a high quality. So surrounding this cylinder are coils and coils, many miles of coils of wire, and electricity passes through these wires in order to create a big electromagnet and large magnetic fields within this machine. Now, the other thing about the machine is that the operator can control the strength of the magnetic fields. It can control stimulation of the object with radio frequency waves, and it can control what radio frequency signals it picks up from the object as well. And one of the advantages of MR, we'll see a little bit more about this as we go through the physics, is that it can be tuned. You can tune the imaging method in order to look at the kinds of things that you would like to look at. Okay? And that turns out to be one of the powerful things about MR. So people are still discovering new ways to look at the resonance between the magnetic field and its effect on atoms and the radio frequencies that are generated to learn how to make new kinds of images. And we'll talk about some of that as we go. So the magnetic resonance that's most done in people for clinical imaging takes advantage of the fact that our bodies are largely water. And all those water molecules have hydrogen atoms associated with them. And so there's a lot of hydrogen in your body. And hydrogen atoms are susceptible to magnetic resonance. And because they contain this dipole moment that will align in a magnetic field. And so what happens in magnetic resonance is that you're placed in a very large magnetic field. Many of the hydrogen nuclei in the molecules within your body align with this magnetic field, and then the machine sort of tips those aligned molecules out of alignment. And if that's done properly, you will start a kind of motion in these molecules, what's called a precession, where the molecules move like a top. And when they are performing this kind of motion within the magnetic field, they're trying to get back to their preferred alignment, but they're doing that in this top-like fashion. If you have many, many atoms that are all processing in the right way, they will emit radio frequency waves that you can detect in this cylinder outside. So this shows it sort of schematically. You have atoms inside your body. These are hydrogen atoms, for example. You place the body within a strong magnetic field, and these atoms align so that they're parallel with the magnetic field, which is going from top to bottom here. You stimulate these atoms with radio frequency waves, and you knock them out of alignment. Now, you can't just stimulate them with any radio frequency wave. That radio frequency wave has to be exactly right for the atoms that you want to move. It has to be radio waves that are at the correct frequency or wavelength to stimulate these particular atoms. And that's one of the things that makes MR so versatile, in that if you stimulate them with one frequency, you can manipulate hydrogen atoms. If you stimulate them with another frequency, you can stimulate other atoms. Now, the reason why most of the images you'll see are based on protons or hydrogen nuclei is because hydrogen is so much more abundant than everything else in your body. And so you get a good signal with that. If you were stimulating other kinds of atoms, you wouldn't get as strong a signal. You wouldn't be able to make as good an image. Okay, so you stimulate these atoms with a radio frequency. They begin this motion or this precession, and this just shows schematically that this precession is like a top. They're out of alignment. The nuclei are rotating, and they're eventually coming back to their equilibrium position, which would be aligned with the magnet again. And so what you measure in the MR device is this relaxation from the excited or tipped position, relaxing back to their equilibrium or aligned position. Now, if any of you go on to study quantum mechanics, or you try to study the physics of medical imaging, particularly MR, in more detail, you'll learn that this simple description I gave you is not entirely accurate. It's not inaccurate, but it doesn't describe the whole thing. It's really a quantum mechanics phenomenon that's happening with the molecules here, and it can't be described completely unless you have the sort of tools of quantum physics to describe it. But this is a sufficient way of thinking about what's going on in here. So what you measure then is the relaxation of these excited molecules back to their aligned state. And you can measure that because as these molecules are precessing, they're emitting radio frequency radiation, which you can detect. Now, so this involves magnetic fields, strong magnetic fields. It involves radio frequency radiation, the kind of radiation that radio stations use to broadcast signals that are picked up by antennas. Right? And so these are generally presumed to be safe for biological tissues. There's no ill effects that we know of exposure to magnetic fields or radio frequency radiation at these wavelengths. And so it doesn't have the same concerns that X-ray radiation or other kinds of radiation, which I'll talk about in a few minutes, have. So this is some examples of MR images. These are MR images that are taken at different locations in the brain. And remember now that the patient is being conveyed on this table into the core of the instrument. And measurements are made only on the part of the body that's inside the instrument. And so just like in CT image, you move the patient through and you take images of different slices through the patient. Now, if the patient is having a brain or a head MR scan, you would just put them in until you went through this part of the body. If you were doing in the abdomen or the leg, you would just scan that part of the body. And this shows then images, transverse images, at various locations moving down. This is nearer the top of the head. This is a little further down. You can see the ventricles. I think actually these two images might be from the same location, but they show you one of the features of MR. That is, by looking at different relaxations or stimulating with different pulses of radio frequency, you can see different kinds of contrast. So in this image, you can see more clearly the distinction between gray matter and white matter. In this image, you don't see that so clearly, but you see better the distinction between brain tissue and the cerebrospinal fluid that's in the ventricles. So the point is that the technique can be tuned to see what you would like to see best, right? And then going farther down in the brain, now you're seeing some of the bones of the face and the cerebellum back here, or a lower section of the brain. So this is a section probably from somewhere in here, and this is even lower down than that. Okay? So these are just examples of some magnetic resonance images. As I mentioned, magnetic resonance is not so good at looking at bone because bone doesn't have a lot of water in it, so it doesn't contribute a lot of signal. But it's very good for looking at differences between soft tissues. And remember, in CT, soft tissues like the muscular wall of the heart and the blood that's inside the heart look roughly the same. And you can't distinguish those well. There's not intrinsic contrast. With MR, there is intrinsic contrast because the properties of those different tissues are different by this method. A newer form of magnetic resonance imaging is called functional MR imaging, and it uses the same machine, it uses the same approach, but instead of designing your radio frequency pulses so that you look at the static structure, you design it so that you're particularly sensitive for looking at flowing blood. And you can actually measure the velocity of blood flow in different regions of the brain. Now you can do that because blood contains a lot of water, and this is water that's not static, just staying in one place in the brain, but it's moving through blood vessels. Right? And you can detect the motion of the blood vessels with this technique. It can also tell the difference between saturated and desaturated blood. What's saturated blood? Here I mean blood that's saturated with oxygen. So it's loaded up with oxygen. Desaturated blood is blood that's had the oxygen removed. Now, if you can measure blood flow and you can measure differences between saturated and desaturated blood, that means that you can monitor within a small region of tissue how much blood flow is going through, how much oxygen is being consumed. So you can measure locally what's the rate of oxygen consumption in a tissue. Now, if you know oxygen consumption, then you know something about metabolic activity in that tissue. A region of tissue that's consuming a lot of oxygen is doing a lot of work. Right? In the brain, if you find regions of tissue that are consuming oxygen, that means those are regions of tissue where there's a lot of energy being consumed. Those are regions of tissue where there's a lot of neural activity, a lot of brain cells doing what brain cells do. Right? So it's called functional MR imaging because through this approach, one can look inside the brain, for example, and find regions that are performing functions. So an experiment that, well, the other thing about fMRI before I talk about the experiment is that instead of just looking at anatomy now, this is a high resolution picture of the anatomy of brain, an fMRI image is fuzzier. You don't have as high a resolution. And that's because you want to take images fast. You want to take images fast. You don't want to wait a long time. And you want to see how the image changes with time. Right? In a static image, when they took a picture of Wilma, for example, they kept her inside the machine for a while so that they could get a really high-resolution image of the structure in her brain. But she was asked to remain very still because you don't want to have any motion. You want just a picture of the statics. In fMRI, you want to take a picture faster, but then you want to look at how it changes with time. Because it's these changes in time that allow you to look at things like oxygen consumption. You have to look over time in order to measure that. Right? So in an fMRI, in one kind of fMRI imaging, you look at blood oxygen level. That's a measure of neural activity. When blood oxygen goes up, neural activity goes up, the extraction of oxygen goes up, and the fMRI signal goes up. So here's an example of an fMRI image. And actually, the fMRI image isn't shown here. The fMRI image would be a blurry one, like the one I showed you in the last slide. But you might find regions where there's high levels of activity, and you would superimpose those on a static image of that same brain. So here, two kinds of imaging were done. One was the high-resolution MR imaging to get a picture of the anatomy, and then this more rapid time sequence of images to find out where oxygen consumption was occurring. And what was discovered was that consumption is occurring in this location here and this location here. And this is known to be a certain area of the brain called Broca's area that's involved in speech. I don't remember whether it's in hearing and decoding speech or in producing speech. I think it's in hearing and decoding speech, but I don't remember. In this particular example, mixed speech was while the patient was being imaged, they were being exposed to speech that included a mixture of languages, both Spanish and English. In this picture, they were only listening to Spanish. In this picture, they were only listening to English. And what you see is that when under the mixed condition, when they're hearing both Spanish and English, there's a certain portion of the brain that's more active than it is with only Spanish and only English. And from this, you could conclude that this part of the brain must be involved somehow in the special activity that was happening at this point here. That is some kind of a mixed language experience. And as you could extrapolate from this, and you could imagine that this approach, where you could look at what areas of the brain become active during certain sorts of activities, certain sorts of behavior, when certain emotions are elicited, has become a very powerful tool in psychology. So you can do psychological experiments while patients are getting fMRI scans, and you can find out what parts of the brain are involved in that kind of psychological response. And so this imaging is teaching us a lot more than just what is the normal structure of tissue, in this case the brain looks like, but how does it really work in a functioning animal, like a person. So that's a very brief introduction to MR imaging. There's a lot more to learn about this. You'll learn more about this, and you'll see some of these instruments this afternoon. And there's more detail in the book as well. A second kind of imaging, which shares an advantage with MR, in that it does not involve ionizing radiation, is ultrasound imaging. And ultrasound imaging is different from the others we've talked about in that there is no electromagnetic radiation involved. You're not using light or different forms of light here. You're using sound to create images instead. And sound is pressure waves that transmit through a medium. When I'm talking up here, my vocal apparatus is creating waves of pressure in the air which get transmitted through the room, right? And you can understand them because the waves of pressure that I'm creating stimulate your eardrums at the right frequencies, and you convert that into sound. Ultrasound uses much, much higher frequencies of sound than our ears can detect. Right? So we detect, I forget exactly what the range is, but up to I think 40,000 hertz or cycles per second is the frequency. And this is in the megahertz range, or millions of hertz range. So it's higher frequency sounds than you can hear. So some have very short of these high frequency sound waves have very short wavelengths, and so they can penetrate through tissues. And ultrasound allows for good imaging of anatomical structure, and it's also a fast imaging method, and so it can allow you to look at motion in ways that are difficult to do using some of these other techniques, and I'll tell you about that. So the way that ultrasound works is you have to get sound waves propagated into the body. And you do that through a special device called an ultrasound transducer. And the transducer is placed right on the surface of your body. It might look like a cylinder, like a probe, that's placed against the surface of your body. And usually not even just placed against the surface of your body, but it's placed with some kind of a gel, a liquid gel, such that the probe comes in very good contact with your skin. And that's because sound waves don't transmit very easily across interfaces. Right? If I put something up between my voice and you, then the sound waves don't transmit as well. Right? You can't hear it. Sound waves bounce off interfaces. So you want to get the sound to go into the skin, you have to put the transducer, which is producing the sound waves, right up against the skin, and you don't want a gap of air in between, and that's why you put the gel. Okay. Now this transducer has a special material in it that's called a piezoelectric material. And piezoelectric materials have the property that if you put a voltage through them, they resonate, or they physically move. And in addition, if you stimulate a piezoelectric material with a moving wave, it will create a voltage. So voltages get transmitted into movements. And in this transducer, the movement gets transmitted into sound wave, is what produces the sound waves that get transmitted into your skin and through your body. Because these piezoelectric materials can both form sound when they're stimulated, and they can detect sound and convert it into electricity when they're stimulated by sound. Then the transducer is both sending out sound waves and receiving sound waves back. Right? So these work basically by the same principle that an echo works. If I shout in the right kind of a room where there's nothing to absorb the sound between me and the back wall, the sound will hit the back wall and it will be reflected back to me. And I will hear that sound some time interval later. Right? You've all had the experience of hearing an echo. The same thing happens here. You transmit sound into the skin and it moves forward until it hits an interface. And sound doesn't move so well across interfaces. Right? So it moves through your skin and it goes down and it hits the bone. There's an interface between materials here that have two different properties: skin, muscle, bone. And on each one of those interfaces, some of the sound bounces back. And since the detector is both sending sound and receiving sound, it sends out a sound wave and then it gets the sound back. And it can determine how long it took for the sound to come back. Right? If I know the speed of sound and I know how long it took for an echo to return, I can calculate how far away the object was that created the echo or the interference. Right? So ultrasound works by sending out sound waves that bounce back, are received, and the machine calculates how long it took for this echo to go out and come back, and then it knows there must have been some kind of an object at that distance away. Does it make sense? So ultrasound creates echo time maps and calculates depths from that. I'm sorry, I'm having lots of technical issues today. Something happened, right? Oh, so here's an ultrasound image of the heart, and it's the heart turned upside down. So this is vaguely familiar to you from a few weeks ago, but the atria are on the top, and the atria are on the bottom, and the ventricles are on the top, and that's just to show you it in alignment with this image here. And so the probe is placed on the chest, for example, and it's moved from side to side at one location. And so what you see is an image of what the probe can see as it sort of sweeps out this cone where the sound is moving. And what you see is that there are boundaries between light and dark regions here, and those correspond to boundaries in the tissue. And so you can see the right atrium. You can see the right ventricle over here. You can see the left atrium and the left ventricle, because the white region is the muscular tissue of the heart, and the darker region is the blood that's within the heart. Now, you'll notice that it's not a sharp image like the images that I showed you with CT or the images that I showed you with MR. It's a noisier image, and there's a lot of sort of white spots or dark spots throughout it. And those are things that are called speckles. It's talked about in your book. But there are random sources of interference with the ultrasound image. The reason why ultrasound is useful is because you can watch things with time, and so you can see motion. In static pictures, it looks like a very noisy image, but if you were watching this in real time, you would see the motion of the heart. And the speckles wouldn't be as obvious because you'd be noticing more how the walls of the ventricle move, for example, in time. And that would be very clear from the image. What would also be clear to you is the motion of the valves. And we talked about the very critical role that valves play in the function of your heart. If your valves aren't working right, you can't make an efficient heartbeat. That is a heartbeat that produces a cardiac output. And so ultrasound imaging has been one of the most used tools for looking at valve disease. In that event, it's called echocardiography. Have You ever heard of that term? Echocardiography, which is basically ultrasound of the heart, and it's used principally to look at the function of your valves. The mitral valve and the tricuspid valve here, if this was a video image, you would see the valves opening and closing in correct coordination, hopefully, with the contraction of the heart. So ultrasound allows you to look at motion, and so to see things that are moving that would be difficult to do with other techniques. You also know, and probably all of you in this room where pictures were taken of you when you were in utero. And ultrasound imaging is a very common form of fetal monitoring now, where almost every woman who is pregnant has at least one ultrasound image taken at some course during the pregnancy, just to make sure that the pregnancy is proceeding properly. And this is an example of an ultrasound image. It looks the same way, an ultrasound image of an infant. This is the kind of machine, the ultrasound imaging machine, that you might find in an obstetrics office. And you can see in this particular case that here's the head of the fetus, here's an arm, here's the torso. Again, it's not a very sharp image. But if you were watching this in real time, as the technician moved the probe around on the pregnant woman's abdomen, you would see the baby moving, and you would be able to distinguish parts much more easily in that way because you're moving both the probe and the baby's moving, and you're seeing things from different angles in real time as it's happening. So this is a very common technique. I wouldn't be surprised if many of you, if you don't have a picture of yourself in utero in your scrapbook, probably your mother has one somewhere. All infants of your age were ultrasound. Ultrasound is also a good technique for looking at flow. And when you look at flow, you're taking advantage of something called the Doppler effect. And you've, in physics, probably heard about the Doppler effect. A simple way of thinking about it is if you're standing on the street and there's an ambulance coming towards you, or a car that's coming towards you and the horn is honking. As the car is approaching you, you hear a certain frequency of sound that changes as the car passes. The frequency of the sound that you hear depends both on the frequency of the sound that's being emitted by the siren and the speed that the ambulance is moving relative to you. So when the ambulance is moving towards you, you hear a frequency that's offset from the real frequency of the siren. When it's moving away from you, it's offset even more. Right? And you can hear that. And so if I'm doing ultrasound imaging with sound waves of an object that's moving away from the probe, I can detect both where it is and how fast it's moving by the frequency of the signal that's returned to the probe. And that allows you to image the rate of blood flow through vessels, and that's shown in this picture here. So you can measure the rate of blood flow through the carotid arteries, for example, and that turns out to be a very useful technique for patients that have cerebrovascular disease. They're getting atherosclerosis or hardening of the arteries in the important vessels going up to their neck that can be measured up through their neck up to their brain, that can be measured using ultrasound. Okay, so those two methods, magnetic resonance, ultrasound, have the big advantage that they don't involve ionizing radiation. Magnetic resonance imaging in general takes a long time, requires very expensive equipment. Ultrasound imaging can be done in real time. You can take pictures, images of the inside rapidly. The equipment is not so expensive. So any doctor's office can have an ultrasound machine. The image quality is not as high, but you can image things that are in motion, right? So these imaging approaches are used for different applications because of the advantages that each one has. I want to talk briefly about nuclear medicine, and I'm going to have to go fast here, about nuclear medicine. And this does use a form of ionizing radiation, in particular gamma rays. Gamma rays are produced by nuclear events inside the nucleus. In particular, they happen when radioactive isotopes decay. When radioactive isotopes like xenon-133, technetium-99, iodine-123. These are unstable isotopes of these molecules. And so with a certain frequency, they will decay back to their more stable form. When they decay, they emit a form of radiation called gamma radiation, many of these. And gamma rays, you remember on the electromagnetic spectrum, they were up there with X-rays. High frequency, short wavelength radiation penetrates easily through tissue, but is also an example of ionizing radiation. Now, the difference between nuclear medicine and what's called nuclear medicine and conventional X-rays is in X-rays, the X-ray source was outside of you, and you were being bombarded with X-rays. In nuclear medicine, the gamma ray source is injected inside of you. And what you measure is the amount of radiation that comes out. Now, what's the advantage of that? Well, the advantage is if I can find radioisotopes that concentrate in certain regions of your body, and I inject those isotopes into you and then measure where they are, I can measure the function of that particular region of your body. And the first imaging that was done in the thyroid. And your thyroid has a very active mechanism for concentrating iodine. And because of that, if I feed somebody radioactive iodine, that iodine will accumulate in their thyroid gland, which is in your neck. And the rate at which it accumulates and the pattern at which it accumulates can indicate whether you have a healthy or a diseased thyroid. And if I then take images of the thyroid after I've injected the radioactivity and I look to see if the radioactivity is there and how fast it gets there and how fast your body removes it, then I can learn something about how your thyroid is functioning because of its ability to concentrate iodine. That's one example of it. But imagine you have a chemical that accumulates in the brain and accumulates only in certain areas. For example, you have a chemical that's related to the neurotransmitter dopamine, and you give it to a patient that you suspect is having Parkinson's disease. Well, Parkinson's disease involves the brain neurons that process and use dopamine. And so if this radiochemical goes up into the brain, it's going to interact with those cells that are involved in Parkinson's disease. By watching how this molecule moves around in the brain, I can learn about how your brain is processing dopamine and if it's responding in a normal sort of way, right? Does that make sense? So the advantage of nuclear medicine is that you're designing very specific kinds of radioactive molecules that you can put into the body. The molecules are designed to illuminate some kind of biological function, not structure, and then I measure the time course of how those objects, how those radio-labeled compounds move through your body. There are several ways of measuring it. I'm just going to show you the simple one here, or not simple one, but a very powerful one called positron emission tomography. And here, the chemical that's emitted is a special radioisotope that emits not gamma rays, but another particle called a positron. And when positrons are emitted, they will move through tissue until they hit an electron. But positrons don't have to move very far. There's lots of electrons around in tissues. And when a positron hits an electron, they annihilate one another, and they generate two gamma rays, which move in opposite directions. And so if I have a positron-emitting substance in the brain, it will emit gamma rays, which can be detected. And because I'm detecting one here and one here, I know exactly where the source came from. Right? I can trace it back along the lines where I detected the gamma rays, and I can find out where the positron emitting element was. And so I can make very nice maps of the brain like these that show you where the positron emitting isotope accumulates in the brain. And this is called PET imaging. I'm going to skip over this one, which tells you a little bit about the economics of these different modalities. Ultrasound, as I mentioned, was cheaper. CT costs more. MR in general costs more. PET imaging costs even more because you have to generate radioisotopes locally at the source too. And so in general, you need a cyclotron or some kind of a machine to generate these radioisotopes as well. And there are other things you have to think about if you're thinking about installing these, is how much do they cost to operate, and how how much do they cost to operate? How heavily do technicians have to be involved in order to keep them working? The last thing I want to talk about is optical imaging. And as I mentioned last time, I think that during your lifetime, we're going to see a lot of new approaches for using light to image inside the body. That's a problem, right? Because light doesn't penetrate through your body. It bounces off. Most of it bounces off, and that's why we can see each other, because we're seeing the reflected light off of different objects. But you can use light to look at biological objects, and you can look at them in great detail this way, and that's what microscopes do. They allow you to use light radiation in order to look at magnified images of biological objects. And we've gotten very good at designing microscopes that allow us to look at, in very sophisticated ways, at biological objects on the stage of a microscope. And this just shows you an image. It's actually very similar to the CT scans or MR scans I showed you before, and that these are different optical sections taken from a pollen grain. A pollen grain is very small, right? And here's an image from the bottom, moving up, moving up, moving up. This shows you all the three-dimensional detail of this particular pollen grain. You can reconstruct in 3 dimensions and see what it looks like on the outside, or you could look and see what it's like at any point in its interior structure. We're very sophisticated at using light to make images like this now on microscope stages. And one can take very beautiful pictures of biological objects like cells with different kinds of optical techniques. This is familiar to you. This is a glomerulus. And I told you what a glomerulus was last week, but this shows sort of the tuft of capillaries inside a glomerulus imaged by light microscopy. Well, how do I take advantage of this kind of microscopy but look at these kinds of images inside people? Well, we don't know how to do that yet, but we do have some technologies for looking at using light to look inside. And the main one is called endoscopy. And endoscopy involves objects called fiber optics. And fiber optics allow you to not only focus light through a lens, but to take that light and bounce it down an optical shaft, right? So I could take a light beam and shine it here into a fiber. That fiber has a special coating on it, which then allows the light to bounce all the way down the fiber. I can bend the fiber, and because the bouncing depends on the coating and not the shape of the fiber, the light will turn with the fiber. Right? This is how fiber optics work, is described a little bit more detail in your book. And so one can design devices like this endoscope. And this endoscope, you can look through this end here. It has a light source, and that light source shines through fiber optics that you can bend around, and that light comes out the outside. If the light comes out the outside, it hits some biological object and then bounces back light, reflects light, and you can see it. And so you can look inside objects where you can put this endoscope. So this endoscope is designed to go, a patient will swallow it. And so this end will go down in their mouth, past their vocal cords, through their esophagus, into the stomach, and then out of the stomach into the duodenum, or the first part of the small intestine. And that's what's shown here. This is the valve that's leading from the stomach into the duodenum, or the first part of the small intestine. And you can see what the lining of the small intestine and the stomach looks like. And so this has been a very important diagnostic approach for using light to image the lining of the stomach. What would you be looking for? Things like ulcers, things like cancers, any kind of disturbance in the normal anatomy of the lining of the gut. And I think you're going to see a lot of new methods beyond this for using light to look inside people as well. I'll stop there. Thanks.